This PowerPoint is on nuclear fusion, and I can't think of a better way to start a PowerPoint on nuclear fusion than with this picture here. This picture is a representation of the birth of our sun, our star, sort of the time when our star was switched on and it started to produce all that energy. So what it is you have this cloud of dust, and by dust I'm talking atomic dust, or atoms, hydrogens and heliums and things like that floating around. And this huge cloud of dust starts to sort of coalesce around one more dense area, and it starts to rotate. And this cloud, as it rotates, will start to condense around the areas where there's more matter. And parts of it, where there are more matter, you'll get the beginnings of planets formed around the outside, these little protoplanets. And they'll accumulate matter by gravitational pull, and they'll grow larger and larger, and they'll form planets. But in the centre here, the star here will have a massive gravitational pull, and it will start to pull all the hydrogens and helium atoms in. And as it grows, this central part, this sort of proto-star, it hasn't quite switched on yet, but it's got some mass, and it's pulling the hydrogen and helium atoms in, and they're racing in faster and faster and faster. And the bigger this thing gets, the stronger its gravitational pull, and the stronger its gravitational pull, the more it's going to pull in. And eventually it gets to the point where this thing is pulling in with so much energy, with so much force, that the hydrogen atoms will fuse together. You'll get two hydrogen atoms smashing together and actually fusing into one larger atom, and that's what you can see here. We've got deuterium and tritium. Now don't worry about those terms, they're just hydrogens. They're different forms of hydrogens. They're called isotopes. So deuterium's got one proton and one neutron, and tritium's got one proton and two neutrons. It's that one proton that makes it hydrogen. So we have essentially here got two hydrogens smashing together and forming a helium, two protons, two neutrons. You get another neutron out of it, and you get some energy given off. So deuterium and tritium are isotopes of hydrogen. And we've got two small atoms fusing together, and that's why we call it nuclear fusion, because they're fusing together to form a larger atom. You might expect to find that helium and the neutron would weigh the same as the deuterium and the tritium, but they don't. Although you've got the same number of subatomic particles, the same number of protons and the same number of neutrons on each side, there is a mass difference. It weighs slightly less. So what's happened is some of this mass has been converted into energy, and that's a good thing for us, because that's the energy that is in the form of light and heat that helps our planet support life. So some of the mass is converted into energy, so our sun is actually getting lighter and lighter as it burns its fuel up. So if we look at the periodic table, what I've just told you is that two hydrogens can smash together to make a helium. So if we smash a helium and a hydrogen together, we get lithium, and so on and so forth. Because of these collisions between smaller molecules, smaller atoms making larger atoms, the rest of the periodic table, all the way up to iron, so hydrogen, helium, lithium, beryllium, follow it across, boron, carbon, nitrogen, oxygen, so on and so on, all the way up to iron. All of those atoms are forged by nuclear fusion in a star. Now, what are you made of? Well, you're a carbon-based life form. You're mostly carbon, and in fact you're 60-65% water, which is H2O. So you're hydrogen, you're oxygen, and you're carbon. There's not much else to you other than those three elements. So the atoms in your body were formed in a star, which has got to be kind of cool. So that's how all of the atoms up to hydrogen were formed, up to iron were formed. The rest of the periodic table requires an even greater energy source than that, and the rest of the atoms on the periodic table were forged in something called a supernova, which is the biggest explosion in the world, the biggest explosion in the universe. It's when a very large star explodes, and that's where all the other elements of the periodic table came from. So all these individual building blocks for matter came from space. Now, we are trying to do this. Now we have power stations, as you heard from the last video. We have power stations where there's a nuclear core, and that does fission. Fission is splitting the atom, and that releases a ton of energy. And you've seen nuclear bombs; those are fission bombs. What we're trying to do, we're trying to make fusion. We're trying to create a little star on Earth. We haven't quite got there yet. It's a very difficult thing to do, and one of the things that makes it so difficult is that you need really high temperatures and pressures to keep this fusion reaction going for long enough to get any power generation out of it. There's a little picture down there of one of the ones in Oxfordshire. They've had some success for a short period of time, but you think about it, what we're trying to do is we're trying to create a star on Earth, and then, not just content with that, we're trying to harness that star and get energy from it. So you can imagine this is a pretty expensive old thing to do. So that's the fusion generator. Now I found this quote when I was looking at stuff for this lesson. Just pause the video and have a read of this quote. I think it's from the Guardian website about the sort of thing that goes on at one of these facilities. Pause it and have a little read of that. Now you've heard of nuclear bombs, which are basically fission bombs. If you split the atom, you get a huge amount of energy from it. But we have, us clever old human beings, we have invented something called a fusion bomb too. Now I just told you that it's pretty difficult getting the temperatures up enough to get nuclear fusion. So what we have here, this fusion bomb actually uses a fission explosion, and that nuclear fission explosion compresses and heats a capsule of tritium and deuterium, and this initiates a fusion reaction. Now fusion bombs can be thousands of times more powerful than fission bombs. They are the biggest bangs that human beings are capable of making. These things are known as hydrogen bombs. And if you pause this video, there's a picture underneath. If you click on that, it will take you to a YouTube video, a pretty cool YouTube video of a detonation of a hydrogen bomb, a fusion bomb. So we can use this stuff in a fairly destructive way, but we haven't managed to find a way of using it creatively yet. If we do manage to harness fusion and make this little mini star on Earth and get our energy from it, it would be clean, it would be pollution free, unlimited energy. It would solve the energy crisis. We wouldn't have to worry about coal, oil and gas running out, and carbon dioxide emissions, and nuclear radioactive waste, and what do we do with it. We wouldn't have to worry about any of that anymore. So it's worth ploughing some money into. Trouble is, these things are extremely expensive. I don't think there is a single country that can really imagine cracking this one on its own. So you have this international joint venture where different countries are all ploughing money and research and knowledge into it, with the hope that one day we can crack this nuclear fusion and use it as a power source. So there we are. That's a very brief look at nuclear fusion.